So the area problem, we've got a function f. This time we're making sure that it's above the x-axis, so when we're talking about area under the curve, it actually sounds like area under the curve. But it'll be the area between the curve and the x-axis on the closed interval from a to b. And that creates an area. So we want to figure out that area. And what we're going to do over the next couple of days is look at this idea of little rectangles and how it forms what ended up being called the fundamental theorem of calculus. Like, sounds important. Okay? So if we wanted to find that area, that's hard to do because of the curve. So what we do is we start making some rectangles. And when we make those rectangles, sometimes the rectangle might be going over top of the curve as an overestimate. Sometimes it's underneath the curve as an underestimate. But if we added up all those rectangles, then that would be a good estimate. And the smaller we make those rectangles, the better the estimate is. And you might be thinking, well, we could just keep going smaller and smaller. And what if you did things smaller and smaller to infinity? Is that kind of a limit? Oh my goodness, it would be. And so our ideas of limits is going to come back into play. So maybe you start to say, well, limits were really important in the definition of the derivative. So we can see maybe why integration and derivatives have something in common. All right, so this is how the approximation of an area is going to lead to the integral. You know that if you make a rectangle, the area is length times width, and in this case, the width times the height. And it's a super easy formula. So if you had a constant function, the area under the curve would be super easy, right? Because it would make a perfect rectangle. So here we got horizontal line. Whatever this width is from A to B would be B minus A. And you would just get your area would be the height times B minus A. But if you didn't have a constant, if you had some curve that you had three different lines, then you would have to add up each of those different areas, and each of them would be a rectangle as well. So, here's our first idea, okay? We're going to have 1/2 x plus 3 as a line, and we're going to look at the area from 2 to 4. Now, just like we saw in Mr. Bean's videos, if you had to find this area, you actually have the geometrical shapes that you could find it exactly. Can you see you could make a rectangle for part of it and a triangle and add up that rectangle and triangle? You would get the area perfectly, okay? But what we're going to do here is we're going to do an underestimate and an overestimate. If we took the first point, 2, 4, and made the rectangle with that height, you would get an area of 8. And obviously that area of 8 would be an underestimate, not big enough. And if you use the endpoint and at 5, you would get an area of 10. And we can conclude that the area should be somewhere between 8 and 10. Because if the underestimate was 8, the overestimate was 10. Does it work out to be perfectly in the middle? Well, because it's a triangle in that little spot, yes, but we're not supposed to know that. We're just getting estimates here. If we took 2 points and we did 2 underestimates, we get 8.5. And this is a much better underestimate than 8. And if we did 2 points and did the bigger rectangles, we get an overestimate of 9.5. And now we know the area is somewhere between 8.5 and 9.5. And even though we could figure out perfectly to be 9, and we know that that's the answer, we could keep going with this and do more and more and more and more. Right? But it seems you can maybe see why Archimedes called this the method of exhaustion. It's like, oh, let's do 100 calculations and add up 100 little areas. And we get closer. But it wouldn't be perfect. It would still be either an underestimate or an overestimate with those ideas. So, the number of subintervals increases, the approximation improves. And we have already said that the actual area of this one is equal to 9. So as you increase the number of rectangles for both the upper and lower sums, the estimate gets closer and closer. So you can see that as a mathematician point of view, this seems like a good idea. Always being lower in one set, always being above in the other one. You're guaranteed that your answer needs to be in between them. And if you can kind of use the squeeze theorem slowly to squish those together, eventually you're going to squish them together to get the actual answer. Okay, so now we get into the beginning of what for you guys is going to be some notation nightmares and some very confusing things for your head. Okay? We've got a point starting here at A. A we're going to call the first point x0. The second point, x1. This notation should, next one, x2. After that, x3. I hope you're noticing a pattern. And then eventually, if you break it up into n intervals, you'll get up to xn, which will be the point B. And all of these along the way, you could pick a random one, random point C, and that random point C is like C sub I, because there's C sub 1, C sub 2, C sub 3. They're like X sub 1, X sub 2. So first of all, if we want to break this distance up into n equal spaces, does it make sense that you take the total distance, B minus A, divided by n, and one of those small sections we call delta x. Okay? Just to further add craziness to mathematics, have you seen a triangle used in mathematics for representing change? Right. I don't know who came up with that, right? Well, what should we use for change? Well, we don't want to write the word change. That's like 6 letters, 5. Well, it's complicated to even count how many letters that is, right? We don't want to write that down. That would take too long. Let's use a triangle. So that is delta x, change in x. So we can find all of our areas of our rectangles by doing the change in x times by, and we have to decide if we're doing upper or lower. You're either taking the minimum of the two or the maximum of the two to figure that out. And that becomes our notation. And since we're adding up so much, our sigma notation would be nice to use. Because it's annoying to write so many, especially if you're adding up 1,000 little rectangles. Wouldn't it be nice if we had a notation that did that? And we do. That is our sigma notation. So for the most part in sigma notation, most of the time you start at 1 at the bottom. And you go up by 1 until you want to stop. The top number is the stopping number. But if you start at 1, then it also happens to be that your top number is how many times you're doing it. Does that make sense? So it's kind of helpful when starting at 1 that this would be n things that we're adding up. But that only happens when I is starting at 1. And then you take all of your different heights and change it by the change in x, which is the width of every single one of those rectangles. And then you would add up all of those areas. So we use the little ci to say those are all the minimums. And we're going to use a big Ci for all the maximums. So we're running into another, like, mathematicians are like, oh, this is going to be a little bit annoying. That means every single time I do 2 points, I have to calculate which one's bigger, which one's smaller, and then do the minimum. Okay, I don't know if you noticed in some of these spaces, like for the minimums, notice that for rectangle 1, we use the right side. And then rectangle 2, we use the left side. I think for the video online, it won't show the projector spazzing. So that's at least good. But then over this increasing section, does it make sense that as we increase, the minimum's always going to be the left point? And then as we're decreasing, now the minimum is always the right-hand side of the rectangle? So we're like, okay, well, maybe we could use some calculus to see where the graph is increasing and decreasing to determine whether we're using the left point for the minimum, right point for the maximum. Don't worry too much. This getting messy, we're going to get messy for a couple of days. And then we clean things up. And for the most part, we're going to work with integration with things that are clean. But the process of getting to the clean part is going through the messy part first. So are you going to be asked to do this thoroughly on the exam? Probably not. Are they going to ask you some parts of it to see if you understand it? Absolutely. Okay. So take a breather, because it's going to be messy and it's going to be like Archimedes called it, method of exhaustion. It's going to be exhausting to like figure it out. Just keep an open mind in the thought process. And so the thought process right now is, if we find all the minimum areas and then we find all the maximum areas, our actual area will be between those. And if we make our rectangles smaller and smaller, it becomes more and more accurate. Okay, so with that in mind, oops. With that in mind, we little c1s for all the minimums, a big C1 for all the absolute maximums. We've got it in sigma notation, we've got it in sigma notation. One of them is an overestimate, one of them is an underestimate. So let's look at an example here. We want to approximate this area A from 0 to 10 using lower sums and 2 subintervals. So 2 subintervals means you're going to break 10 up into 2 sections. Equally, they'll both be 5. From 0 to 5, the minimum is 0. And from 5 to 10, the minimum is 5. Our lower estimate, I hope you can see, is terrible. Okay? I feel like we could do much better than this. Because the first rectangle actually has no height. So it would be 0. The second rectangle has a height of 5 and a width of, height of 25 and a width of 5. Notice, because this is a constant, we can use the property of sums that you could bring it out in front. Okay. Our overestimate. Oh no, we're going to do some better underestimates first. Right? We did 5 subintervals. Now the width of each of those subintervals is 2. And because our function is increasing, it's always going to be the left side for your lower sums. Oops. And you just add those rectangles, 8, 32, 72, and 128 together. It's already kind of exhausting just with 5, right? The notation is exhausting. The prospect of understanding the notation is exhausting. So now that you're tired, let's do 10. Right? Homework is to do that. No, I'm kidding. But obviously, as you can see in the picture, the error is decreasing. The first error was terrible. We were way off. I can tell you in this question, we will be able to figure it out with calculus exactly within like 15 seconds. I can even do the mental math right now and see what the answer is going to be exactly. But we're still at the underestimate of 285. And we still have quite a bit of error if we think about that. So approximate the area under the curve y equals x plus 1 from 0 to 4 using both lower sums and upper sums with an interval width of 1. I'm going to just extend the view here so you can see the picture of lower sums and upper sums. X plus 1 is easy to graph. Because it's increasing, does it make sense that the lower sums are always the left side and the upper sums are always the right side? So if we figured out the lower ones with the formula, we would get 10. If you figure out the upper ones with the formula, you get 14. And because it's a nice straight line, and it has those triangles, you could figure this out just with shapes. You probably can see that the answer is going to be 12. So again, just talking about notation, because I think the notation is the thing that's going to get you the most confused here. Like when we have f of c1, we're saying instead of y equals, this is like f of x equals, that's your function. And c1 is plugging in a value. Okay? And with the little c's, those were always the lower value. So in this case, when you're doing the lower ones, this would be c1. C1 is when it's 0. This point is the minimum between this section, so then C2 would be 1. C3 would be 2, and C4 would be 3. Because you're always figuring out the minimum 1 in that section. Then when you plug in 0 into your equation, f of C1 is the y value, 1. So C1 is plugging in the x value, which is the minimum between the two. And then f of C1 is figuring out the y value, and then if you have the change of x, then you get that rectangle. So just noticing and thinking about what the notation means. This might be something that you have to take some time on your own. Just fight with the notation a little bit. Read the notation, see if it makes sense to you, so that you can write things out on your own. Okay? Because we're going through examples quickly here. But you have to come to understand how the notation works. That's sort of the biggest thing. And then capital C1 is always the maximum. So between 0 and 1, here would be capital C1 because the maximum is this point between there. And this would be C2, C3, C4. But we could find areas of weird shapes, right? 4 sine x plus 1. You could graph that. Has a sinusoidal axis at 1, an amplitude of 4. You could get a graph of that and get an idea what it looks like. Here's an interesting word. Inscribed. So when things are inscribed, they're drawn within something. So it's sort of another way of making sure that you're doing the lower sums if you want all of the inscribed rectangles. So C1 will be here, C2 would be here, C3 would be here, C4 actually skips to this one, right? Because between these two, now the minimum's on the right side, then C5, then C6. And we start to notice that if you wanted lower sums, if your function was increasing, you always take the left side. If your function's decreasing, you'd always take the right side. Oh my goodness. What do I want you to not write down? I'm going to start just because, like, there we go. There we go. I know you could plug that into your calculator and figure it out. Is it helpful to write random numbers down in your notes? I don't think so. So we're going to put a big heart there. It's close to Valentine's Day. Maybe you don't need to write it here either. For those of you that are really want lots of things, I'll post the complete. There, you get 9.21, I'm happy. Do you think you get the idea? That's all I'm concerned about. Right? If I want to exhaust you, I can make you do this. I don't really want to exhaust you because I know we're leading towards a much better method that's quicker and easier. Okay? but it's nice to acknowledge that people in the past had to struggle with long calculations to figure this out. Speaking of long calculations to figure this out, do you know how fun it would have been before a calculator to not only to figure this out have to be like looking up values in a big book for each of these things to see what sign of all of these values would be? Okay, so the idea is you can add up the rectangles. You would have to work to find out which ones are the minimum, but then each of those rectangles, in this case, because you have 6 of them, you take the distance of 3 and divide it by 6, and the change of x is going to be a half for each of them. So now you know the width of each rectangle, and the height is going to be the minimum, and that will either be the left side or the right side of all of those rectangles. Now, if we wanted to find the actual area, because we've been estimating so far, you would have to have an infinite amount of rectangles. And if you did an infinite amount of rectangles, the limit as n goes to infinity of all the small minimum rectangles would equal the area. And the limit as n goes to infinity of all the bigger overestimates would also go to the area. And that would mean that these two limits would be the same. Okay. Step 1, well, almost, we have one more step. All right, I will zoom out so you can see this a little bit better. Are we ready to be challenged? I like the feeling of absolutely not, Mr. Dare, that came from you guys, but here we go. You know, it's going to be, sorry, but we could draw this picture and we could use our regular triangles and rectangles and find this area, I'm going to say in under 10 seconds. Okay? So because we could do it so quick, we want to say, oh, I've learned this new thing about calculus and infinite rectangles, so I'd much rather do this in a much more difficult way. That sounds like fun. Okay, let's do that. Okay, so first of all, I'm going to just show you how easy this would be. From 0 to 10, 3x would look like this, right? Straight line. At some point 10 you'd have here. Oh my goodness, would that make a perfect triangle? And at 10, can you see that this height would be 30? Okay, so we're going to pretend we have no idea that the area of this is 150. We don't know that answer. We decide we would much rather not use our triangle formula because it's, you know, you made a New Year's resolution. No triangle formula till May. I'm going to see if I can go through math without using my triangle formula till May. So I want to find this area, but I'm not allowed to use base times height divided by 2. So I'm like, perfect. I'll use an infinite amount of rectangles instead. So here's our endpoint from 0 to 10. Our change in x would be 10 divided by however many rectangles we want to use. And we're going to keep the number n there because we're going to make n go to infinity. Our minimum in this case, or no, here's our maximum, ci, upper sums, that's a capital C. Lovely that we decided to use C, so that for those of you with great penmanship, you'll never be able to tell if it's a big C or a little c. Okay. Our capital C will always be the right-hand value, and the right-hand values are always x1, x2, x3, so ci will equal xi. So the change in x is 10 over n. CI will be 10i over n. Let's see if we can make sense of that. Okay, if the change of x is 10 over n, that's telling us one of these spaces is the change of x. We are saying that if you wanted to find the third one, you don't have to write this down, but if I wanted to find the third one, does it make sense that I would just go change of x 3 times? Because it's always going to be the right-hand side, because it's increasing. So change of x is 10 over n. If I want to find the third one, I would do the change of x 3 times. Okay. F of CI is just plugging CI in for x. And since CI is equal to xi, F of CI will be 3xi. Right? And at this point, most of you would say what most people do with their New Year's resolution. It's January 2nd. I am giving up on my New Year's resolution. I'm going back to my triangle formulas because this seems like a notation nightmare. Okay? Right? Because most of us probably right now are feeling like, am I lost? Most likely. So this again, you're going to have to take after class, take some time, fight through this notation. Maybe watch the video again because I'm explaining some things. So now if we wanted to find all the upper sums, we would add up all of the f of ci's times change of x's, which, because the f of ci's are 3xi's, and the change of x's are 10 over n, we can write this as 3xi 10 over n. And then since the xi is equal to the ci, I could write the xi instead as 10i over n as well. Simplifying this gives me 300i over n squared. And I just have to add that up from 1 to n. Now, since n is a number, the 300 over n squared would come out in front. And now I'm just adding I up to n of I, which was one of the formulas we learned yesterday. Do you remember adding up the first consecutive numbers? This would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. Okay? And we need to know that that formula is n times n plus 1 divided by 2. Which, if we simplify this, one of the n's will cancel out. 300 divided by 2 will become 150. And so we have our sum of all of those rectangles. We now have it as a formula. The sum of all those rectangles. So if you decided to just use one rectangle, you plug in 1 for n, this would be 2, you would get an overestimate of 300. Look at our picture. If you just did one rectangle, that would use one maximum point, that would be one big rectangle, you get 30 times 10, you get 300. Our formula shows us that. What's nice about this formula is if you decided to do 7 rectangles, right? You could do 150 times 1 plus 1/7 and get that over estimate. But we want to find the actual value, and the actual value of the area would be the limit as n goes to infinity. So as n goes to infinity, that 150 can be pulled out. We are now taking this limit of 1 plus 1 over n. And do you see that the 1 over n when n goes to infinity would be 0? And this just becomes 1 plus 0 with their, I haven't done limits for a while, eh? And we get 150. And we're like, oh, see, I didn't need my area of a triangle formula at all. I'm still good until May with no area of a triangle formula. Because this was definitely less painful than base times height divided by 2. In fact, I think I'm going to do this from now on for everything I want to do. I can see I've converted some of you. Definitely. This is your now preferred method of doing. Right? I can't even look at the area of the formula anymore. I don't need that. I'm just going to use an infinite amount of rectangles from now on for everything.
So under where it said endpoints, why should you put x1 next to it?
Under where it says
Endpoints.
endpoints.
x1 next to it.
So I was just looking at them. The first one would be 0,
Oh,
right? x1 would be 1 change of x over, and since the change of x is 10 over n, 1 change of x over. x2 would be 2 changes of x's over. x3 would be 3 changes of x over. And what we're really looking at here is that xi is 10 changes of x over. I changes of x over, which becomes 10i over n. So it's just getting that pattern to figuring out this common one. Because we use that common one right here, and then it gets plugged into the equation right there. Okay? Yes.
I know what n is. What does I represent?
I represents which iteration you're doing. Are you doing the first one? The second one? Because it shows up, I shows up in the sigma notation, and it's saying, we're adding up a bunch of rectangles. Which rectangle you're on? Oh, we're on the 5th rectangle. Oh, that's when I is 5. The 6th rectangle is when I is 6. The 7th when I is 7. And we keep going that way. Oh, I definitely feel that the vibe in this room is that you are good to not use area of triangles formulas anymore. This makes so much more sense to use, right? Okay. So this is the first iteration of complication. How do we feel? Horrible. Oh.